understaffed today. I think Avi's out of town. I'll be doing some remarks in this place. And a lot of other people from the HD collaboration are also out of town. I think they're in DC. So just as a reminder about that, we're going to have a broadcast here of their announcement at 9 a.m. tomorrow morning. The details are on the blackboard and the wall.
Wait, if you're really going to play Avi, don't you need to beat up on screen theory?
I don't have any opinions about that. Not a controversial. The other thing you did want me to mention to you, though, was that LIGO's their observational run has its first detection of the higher black hole system, and we could probably talk to Cindy for information about that. So our first speaker is Yakov Shlapentokh-Rothman. He's an assistant from Princeton, and he's speaking to us about super radiance and care.
Thanks for the introduction. It's an honor to come here and speak. All right, so as evidenced by my title, I'm going to speak about superradiance, which is a topic, the investigations of which go back to the so-called golden age of general relativity. And while in the intervening years, there's been a lot of progress on understanding it, and I'll talk about some things. One of the points I'd like to make in the talk is that there's some pretty basic conceptual questions about superradiance that where we don't know the answer, and that I think sometimes don't get are not as high profile as I think they can be. So I'd like to make that case for you, but we'll see if I'm successful doing that. Okay, so let's just start with sort of a high-level review. All right, so this phenomenon occurs because of what's known as the ergo region in a rotating curve black hole. So what's the source of this? Okay, so we all know Noether's theorem, right, which says that if you have a killing vector field on your spacetime, there's some procedure, stating it very vaguely, some procedure by which you get conserved quantities. Okay, and these conserved quantities, their usefulness is often dictated by the use of them. It depends on, for example, if it's positive definite or not. And we have this very nice criteria that it will be coercive, will be sort of a positive definite quantity exactly when the vector field which generates it is non-spacelike. Okay, and in many areas of physics, of course, there's a time translation, which is time-like, and that gives you the positive energy. Okay, but as is well known, if you have a curved black hole which is spinning, your unique killing vector field, which sort of corresponds to time translation at infinity, there's a region near the black hole, but outside the black hole, where the field is spacelike. And so, because of this, the sort of your natural conserved energy in your problem doesn't have a sign. All right, and this is, yeah?
What does coercive mean on your slide?
If you want, well, sort of non-negative, but sort of if you want, say, for a scalar field, that the local energy measured by an observer with respect to so the energy defined by this theorem of an observer with respect to some time-like direction, is sort of controls all derivatives of the, is greater than or equal to some constant times all derivatives of the scalar field. Does that make sense? Just it sort of controls.
You're saying energy doesn't have to be positive anymore, for instance.
Yeah, if this is violated. Yeah, I mean, you can just positively. Okay. And so, okay, we in principle have this idea that energy can leak out. Okay. And so this, okay, so that's one thing. This quickly leads to the following physical sort of situation, that, which, as far as I understand, was first sort of noted by Zeldovich, that you can take a scalar field, so propagating on a black hole background, and you can sort of imagine you shoot in, so you're sitting on Pascal infinity, you shoot in a pulse, okay, way out there, sort of energy is positive, it's like, say it's us, everything's normal, then it comes close to the black hole, into the near where this energy can be non-negative, and it splits into two pieces, one of which has negative energy, one of which has positive, and then the positive piece can go back to, can come back out to us. But the negative energy piece, well, it can't come back out to us because, well, you can only have negative energy near the black hole, but it can fall into the black hole. All right, and well, if you think about it, because energy is conserved, if you lost something of negative energy, what came out has to be bigger. Right? This is, so you get sort of some energy amplification.
And then the black hole loses mass when that negative energy piece falls into it?
You may expect that, yes. Yeah, though at this stage you could study this in the context of, say, just you could fix the background, say, and study this problem for simplicity, so you neglect back reaction.
Because if you're thinking about this in the context of energy extraction from a black hole, then
Of course,
if,
yes.
if this thing happens enough, then the black hole will lose a certain amount of mass, and then that process won't be able to continue. So if it's a Penrose process, then there's this
That is
a
indeed,
certain
yeah.
fraction of the
Exactly.
total energy of the black hole that you can extract from that.
Yeah, that's correct. Yeah, I'm just saying that you could, depending on exactly how you're studying the problem. Yes, indeed, that is you expect that sort of the basic model, if you want, that Zeldovich had in mind is something like you have a rotating cylinder, and a wave comes in and hits it. If you sort of fine tune the wave, it can come in and kind of the cylinder slows down and the wave bounces off if the sort of rotations are all aligned. So indeed, you expect the black hole to spin down. Okay, so already here though we can see kind of will be a theme, and the talk is that, right? I mean, okay, this certainly seems plausible, but there's a fundamental tension in this process between the fact that in principle you can split into two pieces, but of course your wave wants to disperse. So it's not as if one doesn't think that it's reasonable that a wave comes in, hangs out close to the black hole, hangs out there for as long as it wants, and keeps shooting in negative energy, and then it gets as big as it wants, then leaves. I mean, in principle, the wave doesn't want to just hang out in one place, right? And so somehow the story is going to be about this battle between this sort of dispersion and this super radiance, and that's what we want to explore. Okay, so let me sort of formally set out the main questions I'm going to be interested in. All right, so at sort of this first round, let's say you've just discovered this phenomena. Let's put ourselves back in the mindset of the late 60s, say, we're interested in things like very fundamental questions like black hole stability. Okay, those seem complicated, but we know that maybe some kind of first step approximation to linearized gravity is just the linear free wave equation, massless wave equation. Okay, that's first thing. And there are two sort of natural questions. So first of all, can superradiance be exploited to extract an infinite amount of energy? And let me maybe, as for the previous question, let me preempt. Yes, of course, in the context of the true Einstein sort of evolution, you wouldn't. What I really mean is that is there some kind of instability associated with superradiance? It's just that at the level of the study of a fixed, of a fixed background, if massless that are propagating, the instability would be reflected into sort of infinite energy extraction. Okay. And two, you can ask, okay, independent of one, is it also possible, you have this weird, again, it's very natural to ask, is it possible to sort of extract, okay, again, you don't expect that you can have a wave just going around, you say, in general, it seems, you can't have a wave just sticking in some orbit for all time because it'll disperse, right? Energy will be lost. But maybe, is it possible that you could balance the dispersion and superradiance to sort of construct kind of time periodic solutions that stay? Okay,
Bound states.
Bound states, if you will. Okay, so these are two natural questions. And all right, so I think sort of the first, some of the first kind of provocative or interesting thoughts in this direction go back to what's known as the black hole bomb, the provocative name of Princeton. And they said, well, okay, this is I'll be revisionist. I'll imagine what they were thinking. They said, okay, right, we have this superradiance effect. We know in general, sure, waves want to escape, but if we just kind of want somehow like a proof of concept? I mean, is it just that the energy is not positive? I mean, is this just like a technical obstruction, or is there really something that can go on? They said, well, let's consider a situation where we kill the ability of things to disperse just by hand. We stick a mirror around the black hole. So now you imagine the wave comes in, it extracts and wants to go out, but it hits this mirror, right? And now we allow ourselves to fine-tune the wave in the mirror. Maybe it can bounce in such a way that every time it bounces, it extracts energy, and this sort of just increases. And okay, so maybe it can do this in such a way that it would extract in principle, infinite energy. Again, in a real system, presumably either the mirror would break or the black hole would stop spinning. But okay. All right, and there's another sort of more kind of concrete reason. And okay, this bouncing back and forth is a nice thing to think about, but another sort of way to think about it is in terms of existence of growing mode solutions. So I just mean that you consider your solution, you can separate variables in this way. These S's are, if you're on a curve space-time, they would be what's known as oblates for orbital harmonics. All right, and you look for a mode solution. So where this omega has the imaginary part of the omega is greater than 0. So that would correspond to it growing exponentially in time. And the relevant boundary conditions would be that it's sort of regular in the event horizon, and you're putting a mirror in your problem is just that it's some constant R curve. You say it has reflecting boundary conditions or something. Okay, and so in this setting, you can find, you can show that there are growing solutions. So this is a successful proof of concept. I mean, this is a real. It's not just sort of some technical issue. There are situations. Okay, here's a contrived situation. There are situations in which the superradiant instability can kick in. Okay, and of course, as I've been emphasizing, this is maybe not so illuminating. Like saying for the case, so an asymptotically flat situation, of course, is very different. But even though this isn't really the focus of my talk, already at this point, for those of you who are familiar with, say, Curry ADS geometry, this doesn't bode very well for that setting, right? Because there you have a sort of null infinity is like a time like that. We often think of ADS as being like studying something in a box. In that setting, it is like there's a mirror. Well, I'll get back to that later. So, but anyway, they're sort of these original motivations were somehow they were thinking about they were really thinking about black hole stability and so kind of trying to imagine obstructions that could occur. Okay, so that makes sense. Okay, so fine. Okay, so then again, in this history of the subject as I'm presenting it, a very important moment came in 1976 when Damour, Durrell, and Marini suggested that there is actually a kind of physically natural mechanism where you can get something like a mirror. Well, it's not exact, but we'll see. Which is to consider a massive stability. Okay, so and at a very high level, this is not so. It's quite simple to explain why you might think that this is a good equation to look at. So of course, massless equations always radiate to null infinity. There's nothing you can do about it. There's always going to be some flux in null infinity, and so somehow there's a certain complexity that's always there. But as we know, massive ones, they in general they don't, and more so it's consistent. You see, you can look a concrete way to see that again is that if you look at these mode solutions, if you consider you can consider the possibility of sort of it allows to consider these sort of boundary conditions of exponential decay at infinity, which again that's just making very manifest when I'm saying that it kind of it turns off. In principle, you can sort of turn off the radiation to infinity. Of course, it's not a proof that the instability occurs here, but just why this is a natural place to look and just to emphasize the difference with the case of the wave equation. And in particular, you see the point is that even, because you might not expect that maybe these instability rates are very small, so somehow for this massive case, even the limit at which the imaginary part of this frequency is 0, so there's no rate, there's no growth, even in that setting, it's sort of the equation is consistent with an exponential fall off at infinity. Right? And that is a sort of important thing, which technically makes it seem more likely that you can construct these. And they also they numerically sort of found evidence for this instability and had some sort of heuristic treatment of it. Okay, so that was an important moment. Okay, but that wasn't sort of somehow their study was just the beginning of the story. And this is really just the beginning of what even today continues.
If you induce back reaction from the gravitational field, then the build-up of the scalar field will be transferred to gravitational waves, right?
The build-up will be transverse.
Site gravitational radiation.
And the coupling
Yes,
between the scalar field and gravity will. So this is not a perfect mirror once you include the back reaction, right?
Yeah, I mean, it's very much in quotes, I guess. Yeah, I just mean here mirror could be the wrong word. A mechanism to turn off
the limit where the gravitational coupling
goes to 0. Yeah. But it's also, it's also it's a bit misleading in that, so this cuts off radiation to infinity, but it's not as if massive fields don't decay or they still disperse. It's just that it's sort of in the light cone, so it can't run away from the black holes fast.
But you're essentially forming a hydrogenic bound state, right? You're exciting hydrogen bound states, and those will have support, non-zero support in the ergo region.
Yeah. Well, they will be non-zero everywhere, but sort of the bulk of it, maybe
Far
might
away.
be very far away. We'll get to that. Yeah, other questions? Okay, so let me, alright, and so this is, again, I am not, without giving you sort of a full survey there's really lots of works, both analytical, numerical, and combinations thereof, in the physics literature, but sort of two of the, say, what are considered sort of important sort of milestones were the works of Detweiler and Zeros-Erdely, who analyzed, who used a in different regimes, they found that the equations were amenable to certain approximation techniques. So in this large mass limit, Zeros and Erdely used sort of a WPB type method. And in the small mass limit, Detweiler used some approximation technique due to Starobinsky. Okay, and then, like I said, there are many numerical works, including there are also some nonlinear works in this context, which are quite interesting. Okay, but without going into that, I do just want to make the point though that these analytical works per se are, even though you might have, in view of the numerics and things, you might be pretty confident that the instabilities exist, but in terms of an actual explanation of why they exist, they're not, they're actually inconclusive. If you look at what's done there, in fact, again, if you from say the numerics, you even know that the instability is strongest when mu times m, this is dimensionless quantity, when this is sort of order 1.
So
And yes,
when you say it's inconclusive, this is only for the massive case. Are you saying even the massless case is
these are, I'm only talking about massive, right?
mass, but the Press-Tucholsky is okay?
The black hole bomb
Bomb,
with
yeah.
the mirror. Yes, those
There's no problem there.
that
Okay.
you can the original work was numerical, but you can
Yeah.
certainly you can give a definitive treatment of that problem.
So these problems.
Yes. And in fact, sort of what you can see, it even follows from the work that in the limit in which the approximation is valid, the instability rate is going away. And so, okay, if for some other reason you're confident it exists, anyway, I just want to just emphasize that these should not be considered as really providing the reasons the instability exists. Okay.
The
Which
stability rate goes to 0 in both
In both
these
limits, yes.
analytical limits?
yes, I believe so. Okay. So, which leads to you could have guessed where I was going with that preamble. So so in 2014 I did a work which provided kind of a sort of a definitive for the regimes it covers a kind of definitive construction of these unstable solutions, and also, in fact, one thing that follows from the technique that I use is also you get an understanding of these exactly time periodic solutions. Again, these are for massive, it's a fixed massive field a massive field on a fixed background. And so it's just some interesting things that come out of this. So from the technique, you get a kind of a bound for this mu times m, what it's sort of which if you want for any, so this m here is the azimuthal sort of this e to the inv dependence, and if you want this bound, so you also have the L, right, and the SML. You can either think that like spherical harmonics in reality they're replaced toroidal harmonics. So this bound becomes sharp as L goes to infinity, for example. But anyway, so you get this sort of intriguing kind of relation for which comes right out of the proof, which in particular has this funny fact that as A, in principle, as A goes to 0, right? Again, I told you need some A to even have any instability, but as A goes to 0, you can also take the mass arbitrarily small, though the azimuthal frequency has to go to infinity, which is sort of this funny thing. So it just says you can start with the Schwarzschild black hole, even a wave equation, a Schwarzschild black hole, nothing's going on. You can just sort of touch it a little bit, turn a little bit of mass, and sort of immediately everything sort of the picture becomes crazy, which is sort of fun. Of course, some other interesting things are that but if you for example, if you fix A, and if you fix the spin A in the black hole mass m, and you take the limit, say, as the Klein-Gordon mass goes to 0, then at some point you're not covered by this. So, of course, this was just, I'm only claiming that they exist in this regime. I don't have, but it sort of raises, is it it's an interesting question whether or not one could show that for fixed spin for small enough mass that doesn't exist. I don't know the answer to that. But okay, and then I mentioned this Kerr ADS that this mirror situation was sort of problematic. Didn't look great for instabilities of Kerr ADS, and indeed, so later Dominic Dold sort of adapted the techniques and showed sort of analogous, proved an analogous situation whenever the so-called Hawking-Real bound is violated. Which basically, if you don't know what that is, again, there's a natural sort of, you can look at the generator of the horizon on Kerr ADS, and under some conditions on the space-time, this will extend to a time-like vector field everywhere, and so you have a positive energy. If this so-called Hawking-Real bound is true. If it's not true, then again, like in Kerr, you don't have a global time-like field. Yeah.
Are you saying that there's only a discrete spectrum of masses for which the instability exists, or that's only the case in which you can prove it, and there may be a continuum of masses? Is this an infinite?
Sorry. Yeah. So now, okay.
So you're saying
might be mistake. So the first statement is that it's an open set where if you can. So this is just the masses. You can show that they're near that value. In reality, so the time, if you want, the values where you have a time periodic solution should be thought of as discrete. Those are each. Well, I'll say something about the proof in a second. Not too many details, but the way it works is that the first thing that's done is you construct you fixate a black hole, the spin and the ADM mass. You can show that there's a discrete family of Klein-Gordon masses where there's exactly a time periodic solution. Okay, that's basically the trick, is to consider that as a sort of eigenvalue problem. And then given each of those, you sort of nudge it a bit, you move some of the parameters around and show that then you sort of, if you move things a bit, you get something that exponentially grows. But sort of the exponentially growing ones are sort of in intervals surrounding, it has an endpoint, this is a periodic thing, and then you get a whole sort of open interval.
And in what regime does the wave equation describe geodesics? Is that large L, or?
There are various high frequency regimes that,
in other words,
in any high frequency regime, you would expect the geodesic flow to be governed, to be related to the behavior of wave equation or Klein-Gordon equation. I'll also say something
because
about that later.
you can make, I guess, can you actually make these time periodic solutions by a little packet of matter? Can you form a little?
Packet of matter. You can think of them as, well, I'll say, you can think of them as wave packets along time like geodesics if you want. If that's
right.
That's not an answer to what
You're saying if I take a mass, like a little object, a spaceship, and it has the right mass, which is given by this formula, I can arrange it such that I excite this periodic solution in some regime.
Yeah, I guess I'm not sure. So you're saying, I'm saying you can take a massive scalar field in this time period. Are you saying for a different matter model or something, or what?
Well, I'm bothered that I can't just pick a particle with that specific mass. So I'm asking you if I can.
But you're asking, is there you have orbit, you have massive particles have orbits.
I guess it's like a relation between the particle's mass and angular momentum. Right?
I'm saying usually you get to tune the energy and angular momentum of the mass. You have a spectrum of particles in the world, and you get to change their energy and angular momentum, but not their mass. So but if I have a spaceship, I get to change its mass. So
you should think of this as a. Yeah, you can think of this as a wave packet along certain time-like geodesics, which are on a Kerr background. You can think of these as indexed by their energy, their angular momentum, and then let's say the Carter's hidden constant. And indeed, these will be there's some relation on the angular momentum and the energy, which allows one. You can think of these as wave packets on certain stably trapped geodesics, which have particular relation between their energy and angular momentum. That's where they are located. The bulk of the solution lives on that. Okay.
We'll talk more about
sorry. Other questions? All right. Sorry. Okay. So like I said, I just sort of mentioned this already, but what's goes into the proof? Like I said, the trick is somehow, okay, again, if you consider, the usual thing is that you think of it as an eigenvalue problem for the time for the omega. That's not a self-adjoint problem, that's hard, blah, blah, blah. Many people have different ways of getting around that. The particular trick in this setting is to look just for time periodic solutions, and you can realize the problem as an eigenvalue problem for the Klein-Gordon mass. That's sort of the one sentence summary of the trick. And then, again, like I said, once you have time periodic ones, you sort of nudge the parameters a bit, and you can show that you get some kind of, you get exponentially growing ones. And, okay, and in fact, also from this proof, there's a sort of, this variational sort of construction behind these time periodic ones, again, naturally lends itself to this wave packet interpretation that I was saying, which I like. I think it's pretty conceptual, so let me explain. So again, I said this in words sort of already. But so what's the idea? So we consider a time-like geodesic, which corresponds to sort of a stable orbit around, say, a curved black hole. There are a lot of these. Okay, so it's time-like, so it's a massive particle. Again, this has conserved quantity associated to the Killing fields, time translation, and axisymmetry has conserved quantities, right? You know. All right, now, okay, so now let's just sort of suppose that we had a wave packet solution. So some kind of solution to, it should be Klein-Gordon because it's a time-like field kind of localized on this geodesic. Great. Okay, and let's sort of furthermore suppose it could be expanded to the mode somehow. Now, then sort of, if this object existed, of course, in some sense the difficulty is why should such an object exist? But anyway, it's sort of clear that, well, in order for this wave packet to track the geodesic, you have a relation, obviously, right, between the azimuthal frequency m and the time frequency omega. They have to sort of oscillate with the geodesic if they want to follow it, right? And okay, so that's trivial. But the point is just that from that omega and m, that suffices to also calculate the flux on the event horizon, right? So you can do this. So you just get you have something sort of global happen, right? The geodesic is way out here. It has these conserved quantities to track it. To track the wave packet, you have these constraint on the parameters. That turns out to constrain what the flux is on the horizon. So you do that calculation, and it turns out that you can find these geodesics where the flux is forced to be negative. So this is some kind of way to think about what's going on. Of course, like I said, technically, of course, why should the wave packet exist? I mean, this is why this isn't a complete argument. But I think this is really a good way to think about these solutions. Okay. All right. So now having sort of concluded this little story, let's go back to the original. The very beginning, right, where I was talking about the wave equation. So after all this thing, sort of one of the points was, okay, you know, we had this black hole bomb with a mirror, that's sort of strange, but then I said, okay, Klein-Gordon, that's a natural physical situation which you have this instability. So, well, now what about the wave equation? Supposedly the wave equation is a model, something very much simpler than understanding linearized gravity. And well, I guess by this point we're pretty confident the black holes are stable, you would think. So what's going on? Well, again, okay, it turns out that there are no analogs of these super-radiant instabilities here. Dispersion does save the day. So this is a result in the full subextremal range of myself with DeFermos and Rodyansky. Okay, then it turns out that dispersion does save the day. But okay, that's fine. I mean, that statement per se is not. Again, we expect black holes are stable. Fine.
Is back reaction turned on in this theorem?
No, certainly. Again, this is all for a fixed a field propagating on a. Sorry, I keep saying fixed field on a fixed background, linear field propagating. But again, this seems like some step, like -10 to black holes being stable, right? Okay. All right, but I claim that even sort of. Okay, this is where I said I claim that even here there's some conceptual sort of. Okay, even though I know how to prove this theorem. And in many aspects of it, I understand physical mechanisms behind it, but the real question of why there doesn't exist the super-radiant stability, I don't have any compelling, I've never heard a compelling physical explanation, which, so let me sort of get to. Okay, so first I'll give you a sort of a kind of, well, what I sort of claim is a bait and switch explanation. So I made this case to you that these unstable massive fields can be considered as sort of bound states around these stably trapped time-like particles. You did this weird calculation, they were kind of forced to extract energy by looking at the particle. So you can do that same calculation with the wave equation. Of course, now you have to replace null geodesics, right? Because it's massive. And then it turns out that the energy is always positive for those. So if you take any trapped null geodesic, formally do that comparison, the conserved quantities thing, it turns out that this is sort of what we say trapping and superradiance are disjoint for the wave equation. That's sort of the phrase. And this This I like. This is sort of a reason I can understand. This fact, some version of this fact, is used in that proof. Very important. However, if I want to be really honest with you, that's not really a full explanation. Because one, that's only valid in some kind of high frequency limit. That's telling you certain kinds of high frequency solutions of the wave equation won't have, and there's a very particular kind of superradiant stability that happens. That doesn't tell you in general why.
And you want an explanation, and the explanation typically would be that the black hole bomb mechanism doesn't work unless you have something to find the instability. That's what you want to say, right? I mean,
Well,
if you don't have a bomb mechanism.
I understand that you can check that it just doesn't happen. And you could say that, well, it doesn't happen because the waves go away.
Yeah.
But I mean, well, so one thing, so here's again, not to get ahead of myself, but here's a fact. So you can take the wave equation on any sub-extremal curve spacetime, and you can add to it you can take a positive potential, which is compactly supported, so just supported in a tiny range of R, and you can even put it way far away region of the black hole. You can put in such a potential and create superradiant instabilities. So if you want, so what's special about it being the exact wave equation versus the wave equation plus positive? But supposedly those are not very nasty things to add.
If the mirror is at a large distance, then the instability is very slow, and then it goes to infinitely slow when the mirror is pushed to infinity.
But this is just a single bump. It's not a Klein-Gordon mass. Like a mass is something that's like you cut it off infinitely. I'm saying just a single bump kills it. And because that also, the thing is, like, if you put a potential, like, and the high frequency limits of those equations are the same, so you can't explain it with geodesics.
Yeah.
I mean, I understand what you're saying, and I can, I can come up with such explanations in that spirit.
I don't understand what you said about this potential. Can you draw the potential?
Well, it's just a bump. I'm just saying.
Far away from the black hole. So you have a massive.
Yeah, here's R.
In this setup, you have a massive.
No, this is for a wave equation. I mean, let me just go to the.
Just for massless.
This is a theorem of Moschi's. Yeah, I just mean for massless. So you can put a positive thing here. It's very like super. The ergo regions.
So you're not. It doesn't. So now you have a superradiant stability with this. Okay, good.
And I'm just saying. I mean, this starts seems kind of weird.
Isn't that the same thing as what you're saying though? You're providing a mechanism to confine waves for some period of time.
Yeah, but why in the wave equation? There's back reaction all over the place. It's not like there are effective potentials everywhere. Why is it for the wave equation it doesn't happen?
So your theorem says some solutions for the potential. Do you know for a fact that it's as simple as that, or?
Yeah, it's explicitly given. Yeah, it's not yes, it's a simple potential. Is it really something like this?
And how fine-tuned is it? Is it generic?
Well, you have to. Once you have the mode, then small perturbations will maintain the mode. And for the wave equation, somehow a small potential added to the wave equation there will not be a mode, because these things are all kind of stable.
I still feel like I'm missing something. Like this is, I mean, if I shoot a wave at this, there's a transmission probability and a reflection probability, and then you can compare that reflection probability to the amplification at the from superradiance. So isn't that just all the physics behind this?
Yeah, but I'm saying, but why for the actual wave? What's special about the actual wave equation that something problematic doesn't happen? Because the way think about all the analysis, the way you expand in the large R region, you always think of it as like, say, a flat wave equation plus some potential, right? So I mean, I'm just saying that there are effective potentials all over this problem. There's backscattering. Things are moving around all the time. And I'm just asking for some explanation of what's special about the wave equation. Because the only way, if you want, going back here, like I said, I know how to prove that theorem. So here's the only thing that I know, which goes back to work of Whiting, which is very late, by the way, 1989. It says, so suppose I have an unstable node solution for the wave equation. Suppose I have an unstable node solution for the wave equation. Say that for. Then here's what I would do. This is a crazy thing. I take my R and multiply it by this junk, some kind of sort of like a Fourier transform. With these things depend on the frequency parameters showing up. There's some complex numbers. I do that integral. I multiply it by some other junk. I get an R tilde. this thing, and then I can reconstruct this solution. So I told it just happens to satisfy. There's an effective equation it satisfies. That one happens to have an energy estimate, so it's okay. That's the extent of the understanding. I'm just saying that this does not seem like an explanation. And where do these? I've never where do these transformations come from? What's the source? I mean, or if you want, like, if I'm in another situation, a similar situation, I mean, what kind of features in higher dimensions, or like what qualitative features should I look at to expect that they're existing? Because again, this is about stability. This is such a central question. This is the most basic model problem, the wave equation about the stability of a curved black hole. And I think this is completely mysterious. If this was false, it would be unstable. Okay, and that's sort of one of my. I don't think this gets a lot of attention. And I understand that you can say, well, it doesn't happen because the waves disperse. But okay, I claim that I'm not satisfied.
So I don't understand. I'm very confused. You're
Yeah.
saying given a solution to an equation which is unstable, you can now create a new solution to a new equation which is not unstable.
Yeah. So ergo, the original thing didn't exist. Sorry, I guess that this is an argument by contradiction. So you want to claim that there are no unstable solutions for the wave equation.
Yeah.
So you say, okay, suppose one did exist.
Yeah.
Then, well, I could do this transformation, and then I could construct a solution to another equation.
Yeah.
But that equation, this new equation, now there's sort of no ergo region, and it just has an energy estimate, which is good.
So it's a proof by contradiction.
It's a proof by contradiction. So I mean, it's a very strange thing. Okay, it works. It allows you to prove that other theorem. There's not like a
I
problem
see.
in
So
the logic.
you're upset that it's a proof by contradiction and not a constructive proof.
Well, also that there's no. I just seems mysterious to me. Another way to say, I have no idea what other situations I would expect this to work.
I mean, you shouldn't be too surprised when you try to prove that something does not exist that you get a proof by contradiction. Why does that bother you? I mean,
well, look, in so many other for example,
it doesn't exist because it contradicts something else. That's why it doesn't exist.
No, but I want a physical. I'm just saying, give me a physical reason from first principles why the wave equation has no exponentially going solutions. Because the standard reasons that apply in other settings, because there's something's unitary, so like L2 norm can't grow. That doesn't work here. I'm saying you can say something about high frequency behavior dispersion. All right, that's fine. The high frequencies, and I know how to use that fact actually to use it to prove things. But it's only valid for high frequency part of the solution.
I see. So you want to, if you had a physical interpretation for this, you'd be happy.
I would be totally happy. I've asked many people. I thought about it too. Wait, so I should stop soon? Yeah, soon. Okay. Yeah, maybe that. I'll end
And maybe owing to the protest back and forth during the talk, we can just limit it to one question. Anyone?
So you said the periodic solutions. You got a spectrum of discrete spectrum of masses, right? And then you said you could perturb away from those eigenvalues and get a range of unstable solutions. Good. So how broad is that unstable range compared to the distance to the next eigenvalue?
Well, in terms of what is in terms of what I proved, there's something very small. But in terms of what's true, it's kind of interesting. I'm not totally sure, but I think you could expect that. Yeah, it's sort of what's the. So okay, I have to get this right. We have something like this, and sort of the equation has this there's this really important point where. So let's look at this as a graph of the frequency, the complex plane frequency, and there's this really important point. There's this really important point where at mu, this is the singular, like omega equals mu is a very singular point for the ODE. And so you have these discrete settings, and then what happens is, sort of, if you want, it's some branch like this. Okay, and I, what I prove is something about that this exists. In reality, what you can imagine is, there's some you could sort of continue this curve. I didn't follow this through, and it could be that, and what you can also, I think, you can prove is somehow that they can't come back down. So I think they can't come back down here. So I think the natural sort of I didn't follow this up carefully. But what I expect is that they collapse into here actually into this.
The whole range is unstable.
Yeah, that's
okay.
I don't know, and also you could have people I've looked at these things
But
numerically.
what about the next few
So I,
periodic solutions? Each of them you think might have a whole range?
yeah, that they might collapse into this point. Yeah, I'm not. I don't even want to call that a conjecture, but I think yeah, I'm a mathematician, I guess. So. But I think that's plausible.
Okay, so let's thank Yakov again.
Very good. So our second speaker is Professor Roberto Emparan from University of Barcelona, and he will tell us about cosmic censorship violation.
Okay, thank you. It's a pleasure to be here. So yeah, I'm going to talk about cosmic censorship. And let me first tell you what I mean by cosmic censorship. I have to warn you that in this talk I will not attempt at mathematical precision. It will be mostly physics kind of talk. So for me, cosmic censorship is a conjecture, something that still don't have a full understanding of, that connects low energy physics to the highest energy physics. The idea is that cosmic censorship, the conjecture asks, is whether if you start from an initial situation, you have some Cauchy surface with low energy densities, and then well, you evolve this in time, can this initial configuration take you to a configuration where you have Planck energy densities in a quick classical time scale? I will not talk about infinities. Everything will be, we have a Planck energy cutoff or Planck distance cutoff. That's, so a singularity for me won't be something where things go to infinity, but something, a place where you reach Planckian scale curvatures or energy densities. And the cosmic censorship conjecture says that well, you cannot do this. If you start from low energy densities, you cannot reach these regions, at least not seen from a large distance. So, very often, people say that violation of cosmic censorship would be a disaster. It would be something that we wouldn't want to have. Just because well, if this happens, then well, classical GR breaks down because you're reaching a regime of quantum gravity, and then well, you don't know how to proceed. So then that's a breakdown of the predictivity of the theory. But then, on the other hand, you might think that if you can violate cosmic censorship, then if you start with some situation where you have initial low energy densities, if you can quickly get to the regime of quantum gravity, well, that's better than an accelerator. So maybe it's an opportunity if you're a high physicist, but on the other hand, maybe it's something that if you're interested in quantum gravity, in holography, maybe that's something that might be a problem, because if you're concentrating a lot of stuff with all its information in a region that's smaller than the size of a black hole that would have that mass, then you're in risk of violating entropy bounds. So it's not clear whether, if you want to take a positive or a negative view on cosmic censorship violations, well, it's not clear. It may depend on what's your interests. But at any rate, I think it's fair to say that cosmic censorship is a question that refers to what does nature do when we take it to its limits. When people talk about cosmic censorship, there are two different versions of it, at least, that are usually distinguished. One of them is what's called weak cosmic censorship, which means that well, this breakdown of predictivity, these naked singularities, cosmic censorship is violated, then they can be seen by observers at asymptotic infinity. And then there's another version, the strong cosmic censorship conjecture, which says that well, in this case, if you violate it, you can observe regime of quantum gravity, but and you can have it in your past, but maybe in this case you have to jump into a black hole interior. So this is, without jumping into the interior, this is alone. I mean, the black hole interior, the one that I'm going to talk about today, is the weak cosmic censorship conjecture. So we know already, we know of situations where we can reach Planck energy densities starting from smooth, low energy situations, but then the problem is that we have to wait a long time to get to those regimes. And what do I mean by this? Imagine that we have some configuration of matter, like a cloud of matter, some stellar field, whatever, we let it collapse. The typical time scale for this collapse to occur is given by the light crossing time. Okay. So this is the light crossing time which governs the time scale for classical processes driven by classical general relativity. But on the other hand, we can have, if we have some situation where we have quantum effects, like for instance black hole evaporation. In this case, we know that we can form from smooth initial configuration, we can form a black hole, then we let the black hole evaporate. Then, near the end of the evaporation, then we will reach a regime of Planckian energy densities. But the problem with this is that, well, for a stellar mass black hole, this is on the order of one fractions of a millisecond. But so this is something that's a quick evolution. But this evolution, this is slow quantum evolution, it's driven by quantum effects. The typical time scale for a black hole to reach the final stages of the evaporation, it's well, for a stellar mass black hole, is much more than the Hubble.
Why restrict ourselves to consider black holes at large? Why not Hawking stars or very, very small black holes?
And so, I mean, if it's something that is whose mass is above, I mean, orders of magnitude above the Planck mass, of course you can reduce this time. But I mean, that depends on what you want to do. I mean, what I'm saying here is that there's a parametric separation between these two.
But since the quantum time scale is inversely proportional to black hole mass, you can get an arbitrarily small time scale to evaporate the black hole if you go to a small enough black hole.
If you go to a Planckian, I mean, if your black hole initially already has Planck energy densities, well, then you're already there.
Okay.
I mean, if the goal is to create out of something that's smooth, if your initial system already has large curvature, this is what you're telling me, that you can have small, then of course there's no problem in getting to large curvatures because you're already there.
But maybe not quite Planckian energy densities, but a little bit. So I guess it's a question of regimes.
Yeah, what I'm here talking about is parametric separation. If you're talking about, say, numbers, actual numbers, if you start with a black hole that's, say, 1,000 times the Planck mass, is that a quantum black hole or is that a classical? I mean, that's a question of matters of status of gray, right?
So the gray area, it's a...
But so what I'm talking about here is parametric separation. In this case, there's a parametric separation between these two regimes. So when discussing cosmic censorship, there are several issues that tend to arise. One of them is whether, in order to get to these regimes, you have to fine-tune your initial conditions. And that's something that's quite often discussed. But something that's much less discussed, but I think it's important, is if you have some candidate for a violation, and you have something to claim is a violation of cosmic censorship, strong cosmic censorship, or weak cosmic censorship, sorry. What is the strength of the violation? What is the strength of the breakdown of the predictivity? And this is what I'm going to mostly focus on. But let me first say something about the fine-tuning of initial conditions, and we will see an example where you start. There's a claim, I mean, it's something that's accepted a claim for a violation of cosmic censorship, where you start with some distribution of matter, then you let it collapse, and then you form a naked singularity. The thing is that in this example, it's the problem of critical collapse, critical collapse. In this case, well, you have to fine-tune your initial data. You have to take initial data which are very precisely adjusted in order to reach a regime of Planckian energy densities. Now, sometimes people say that if your initial data cannot be generic, then this is not a valid violation of cosmic censorship. I disagree with this. I think it's valid, but the interpretation is something different. The interpretation is that in these cases, if you have to fine-tune, then this is something, a process that won't happen spontaneously when you look at the sky. You won't find it everywhere. It will happen only very rarely. But then, I mean, this is something that it's, well, in order to observe this violation of cosmic censorship, these Planck energy densities, you don't have to do observations. What you have to do is experiments in the lab, because experimentalists, what they do for a living is fine-tuning. Okay? That's, I mean, you ask them to construct this initial configuration of matter, fine-tune it, and then, well, you let it go, let the classical gravity do its job, and then, well, you're there. Okay, so that's the difference between fine-tuning and normal. It's not that the violation is not a good one, it's simply that it's harder. It's something that you have to hire a team to do it. A team of experimentalists. For the other one, you hire a team of astronomers. Okay. So let me propose something, kind of a strength index now for violations of cosmic censorship. Because there are, imagine that you start with this initial amount of mass m, which is a classical large, it's much larger, something that's much larger than the Planck mass. And then you let this system evolve under classical evolution, and then you form some singularity. Now, say that you have some way of characterizing what's the mass contained in this singularity. That's something that may be a problem. You have to, I mean, there are, like all issues in cosmic censorship, finding precise definitions for everything is almost impossible. Single definition almost never captures all of the physics involved in cosmic censorship. But let's say that you have some way of characterizing, at least for some of these singularities, a way of characterizing their mass. Maybe it's perfectly symmetric. It could be something like Misner-Sharp. You can choose. You can take your pick. But say that you start with this mass, then part of it goes to the singularity, forms a singularity, and the rest of the mass is not part of the singularity. Then what I say, I will say that you have a very strong violation of cosmic censorship if this index here is of order 1, which means that most of the mass that you started with ends up into these Planckian energy densities. Whereas if this index is 0, then you start with a with a solar mass, and out of this solar mass, only a Planck energy, a Planck amount of energy, say 10 to the minus 5 grams, form the singularity.
I'm sorry, I didn't quite follow that.
Yes.
What is capital M with no subscript?
So capital M with no subscript is the initial mass that you start with, the initial data. Okay. And this is the amount of the fraction of it, or the part of it that goes into the singularity. So if starting, as I said, with a solar mass, you get a singularity that has 10 to the minus 5 grams in it, then that's a mild violation. I will say that it's even something that's completely harmless. So, do we know whether cosmic censorship is violated or not? Yes. We have good examples of violations of cosmic censorship, and I will discuss some of them now. The three examples that I will discuss, one of them is a critical collapse, then another one that, so this happens in dimensions 4 or larger. These ones happen only in higher dimensions, the evolution of the dark instability, and then a new one which happens in black hole collisions in a high enough number of dimensions. So critical collapse, this was discovered by Matt Chopwick in the early 90s. This is essentially what I said before. You consider a scalar field, could be some other matter, but you consider a cloud of scalar field, spherically symmetric for simplicity. Then, well, you let it collapse under its own weight. And then, well, it turns out, you can construct a one-parameter family of initial conditions. Say you change this parameter, parameterizes the amplitude, the initial amplitude of your scalar field cloud. And then what happens is that if the initial amplitude is small, well, the cloud just collapses and bounces back, and then, well, disperses away. But if the initial amplitude is large, well, then you have a very heavy cloud that collapses and then forms a black hole. And if you're close enough to the boundary between these two regimes, what Chopwick found is that in this case, the mass of the black hole scales like a power of the distance to the critical point. This is why it's called the critical collapse. And then, well, if you fine-tune your initial data so that the amplitude is within some distance from the Planck mass, which is going to be a distance that's going to be a power of the ratio between the mass and the Planck mass, then what you form is essentially a Planck mass object, which you may call a black hole, a Planck mass black hole. Of course, at this stage, if we have really a Planck length in the game, then this is not properly a a classical black hole is something more like a Planck mass singularity. Now, as I said, in this case, you need fine-tuning. It's power law fine-tuning. But then, as I said, you hire your team of experimentalists to build this cloud. And it's a mild violation of cosmic censorship because in this case, what you form, you start with this large cloud of the scalar field with a macroscopic mass, and then you form only a tiny, a Planck mass object with this very large energy density. So this, in this case, the strength index is 0. But it's, I think, this is accepted as an example of a violation of cosmic censorship. The fact, I mean, people often reject it because you need fine-tuning, but as I said, I don't think that this is a good argument. The next example that I want to discuss is the evolution of black string stability. So these are objects that exist in 5 dimensions. You take a black string, it's built out, you take the Schwarzschild black hole, you stick in a 5th dimension, so the original black hole, which was at a horizon which was a sphere, now it's a sphere along a line, and then this is the initial object that you have. And I don't know what, I have to ask these guys whether they are colorblind, because this to me is a green string. But, well, they call it a black string. Okay, so this is a simulation that they did, a numerical level simulation of the evolution of a black string. You can find the video on YouTube. What they found is that, well, I mean, it's something that it took them a month in a supercomputer to run the simulation. But what they found, it evolves like this, and then you see that here, you have something that's becoming thinner and thinner, the curvature is growing and growing. Here, in the region close to this neck, you find that the curvature seems to be diverging.
What
happens
if you compactify this picture on the 4-dimensional problem?
Well, what you find, this excites the Kaluza-Klein modes, so it's something that doesn't look 4-dimensional, and you have the massive modes, the massive Kaluza-Klein modes are all excited here.
So the curve, so still something divergent, right?
Yes, yeah, the dilatant.
So now it's in the matter, not in the.
Yeah, in that case, yeah. Well, you have.
I'm just asking why in the 4-dimensional picture.
In the 4-dimensional picture, so this doesn't look. I mean, the 4-dimensional picture is not a good one because you're exciting all the Kaluza-Klein modes, so it's effectively decompactifying. But if you insist on a 4-dimensional description, then you find well, singularities in the geometric part and in the matter part. And things go on. So in this case, well, this doesn't need any fine-tuning. Sometimes people say that, well, since you're starting from something that's stable, that's unstable, then you have to fine-tune your initial conditions, because if you're starting from something that's, you have to balance at the tip of a.
In this example, though, is it even clear that you can just make this initial condition?
You can make the initial conditions. I mean,
what do I mean by that? Can I take matter and collapse them and form a black
Yes.
string that then becomes unstable?
Yes. Okay. Yes. So you form the black string. You have to do a little bit more. You have to. So I mean, you can start with a black string which is stable if this is a compact circle and if the compact circle is short enough. So you form your black string, which is going to look like a black hole from the 4-dimensional perspective. It's short enough. Now you want to make the compact circle longer. Can you do this? Yes. And you take the size of the compact circle is a scalar field, call it a dilaton. So you send into this system a dilaton wave, which is, if it's small enough, then it's not going to be much absorbed by the black hole. It's going to make the circle grow and grow and grow until the system becomes unstable, and then you trigger the instability. And this is something that you can do with an open set of initial data, if I want to talk like I know mathematics. So, I mean, this is a weak violation again, because the region where you find this is a small region. It's a very tiny region where the curvature blows up. So it's a weak violation. You start with this large black string, and then you get a tiny region, a tiny amount of negative singularity, of Planckian energy. Now, the next example that I want to discuss is more recent. It's something that happens when you study black hole collisions in this is higher dimensions, not high definition. Which, I mean, black hole collisions, I think they are the quintessential phenomenon of general relativity, because general relativity, at least in vacuum, it's a theory of black holes and gravitational waves, and this is what we're going to cover here. It's also a neat physical picture. You don't have to deal with these fancy black strings and this dilaton wave and whatever. These are just black holes. We don't understand black holes. It will be a mild violation, and we will not require fine-tuning. This is something that we can work with Thomas Andrade, who's a postdoc in Barcelona, and David Lichtenberg and Univ students. So, black hole collisions in higher dimensions, what you do, if you collide them, and then the initial total spin, you have to, you can have initial spin because the black holes are spinning, or because you have already angular momentum. What we find is that if you collide them with low enough total spin, then, well, this is what they form, they collapse and they relax to some rotating black hole. This, by the way, these are results of a simulation. These are numerical simulations that we've done, but not in full general relativity. We've solved this in a limit of general relativity where the number of dimensions grows very large. This simplifies the theory a lot, it simplifies the calculations a lot, and all the calculations that you're going to see, all the animations, I did them yesterday in my computer here. Okay, so you don't need a supercomputer. A simulation like this may take a minute. But it's solving the Einstein equations in a practical way. By the way, there's no gravitational radiation in this limit. This is going to be important. Now, this is the initial spin is small. If you have larger spin, what do you find? What you find is that in this case, something like this. You form the black holes collide. The spin makes this object develop what's called a bar mode instability. So you saw this bar-like object forming, and then this bar-like object forming that forms. It's a bit like those black strings. It's elongated, an elongated configuration. It's unstable like the black string was, and then this instability grows, and one begins to get here larger and larger curvatures.
Does it actually split apart?
We will see.
Does this limit of the theory still satisfy the area theorem?
Yes.
It does?
Yes. That's good. All
It's
the
good,
classical general relativity Einstein equations.
Just higher dimension.
Just in 6 or more higher dimensions. Yes. Yeah. Okay. Yeah. Not for light yet. But still. So we have strong evidence of this by studying this in the 1/E expansion. But we also want to, since we found this evidence, now we're working with people who can do actual evolution, numerical evolution of the full Einstein equations at finite number of dimensions, and this is something that we hope will be reported on in the near future. So we find that a negative singularity forms when this neck grows at the middle of this kind of peanut-shaped horizon. So that's a Planck curvature region. So we have a violation of cosmic censorship. We don't need fine-tuning. We can play with open sets of parameters. We can change as long as we have enough initial angular momentum, then we get there. And then we can do this with initial spin of the black holes, changing the impact parameter. And what I like about this is that it's a very physical process, except for the fact that it requires a few more dimensions.
But your guess would be that this doesn't exist in D=4.
In D=4 it doesn't exist. Yeah. The reason that it doesn't exist is, I think it's interesting, because in higher dimensions, the gravitational potential falls off more quickly than in 4 dimensions. So this means that the attraction is, the gravitational force is kind of looser. Whereas in 4 dimensions, it's longer range, and then it tends to pull everything together and make it more spherical. Whereas at some distance, it's a bit like what happens in neutron stars also have these instabilities, but then, of course, the gravitational attraction between different parts of the star are weaker than what it is in, say, a more compact object like.
So in 10+1 dimensions, then we're really good.
In 10+1 the Planck dimensions, this will be. We think that it will.
So
be
it's our universe then.
Yeah. So yeah. There are realistic dimensions enough. We can go. Yeah. You say. We think that this should be present at least in 7 dimensions, 6+1. Maybe, maybe also in 5+1. We don't know. That's something that we don't have precision. But I think that in 10 dimensions, 11 dimensions, this will be present. So we have these examples: critical collapse, the evolution of a black string, and the evolution of that black bar in the collision forming the collision in the evolution of the collision. The evolution stops. GR stops because you get to a region where the curvature grows up. Okay? So it looks like you're losing predictivity. And this is what cosmic censorship is telling you about. But can we say more about how you lose predictivity, how much predictivity you lose, and whether you can do something about it? So, for this, we're going to go to the similarity and try to see whether we can go beyond. And we will see that even if predictivity is lost, we can regain it. Okay. Yeah. So, the violations that I told you about, they are all mild. I will say that we can have a plausible evolution of these systems with a very small, parametrically small loss of predictivity. So, what do we do? So, as I was saying, we form a Planck-sized neck or a Planck-sized black hole here. This is an object that we're approaching to classical evolution with a surface gravity which is very large. You can say that this has a large Planck scale temperature. What can this object do? What can a Planck-sized black hole do? There's nothing preventing it from just decaying, unless there's some conservation, some conserved quantity that prevents it from decaying. This is going to decay by emitting a few Planck energy quanta. So you have, in some region, you have maybe 5 Planck masses, Planck energies. So this object, just like we think, many of us think that a black hole does at the end of its evaporation, it evaporates in the end by emitting just a few Planck energy quanta.
So how long would a Planck-sized neck last?
A few Planck times.
So it's long enough to radiate? Or...
A few Planck times, that's extremely small time. So this happens classically in 0 time. At the quantum level, it happens in a very small time. So this is going to last just for 10 to the minus 44 seconds.
And if this, well, okay. So would that be enough to even emit any quanta?
A few, yes. You just have the time to emit a few quanta, a few Planck energy quanta, which is what you have in that situation. Now I said that this is a bit like the endpoint of Hawking evaporation, but you may worry, well, but we know this, and there's all the problems of the black hole information paradox and blah blah blah. Here we don't have those problems, because the problems of the black hole information issue, they appear because you have some object that's evaporating, emitting radiation that's entangled with the black hole and so on for a long time. So it's the quantum evolution of the system that gives you all the black hole information headaches. Here, it's the classical evolution that takes you there. There's no entanglement with anything outside. You have this black stream that's evolving classically, very quickly, to that point. So there's no problem with information here. Okay? So it's because it's classical evolution that's taken us there. So it's better than the endpoint of Hawking evaporation. I think that this object really has no chance other than just evaporating. So in the case of a critical collapse, what I'm saying is that we form this Planck-sized object. It's going to evaporate in a time of the order of the Planck time. You need a few Planck quanta emitted, but the rest of the scalar cloud, which is way, way larger, just put numbers. This is 10 to the minus 44 seconds, 10 to the minus 5 grams. That's being in the mass here, and then you have a solar mass. And the scalar cloud just proceeds unaffected by the fact that you have a few Planck quanta that are dancing around. But the evolution is perfectly smooth up to these effects. In the case of the black instability of the equation of the black holes, what we're saying is that what these objects do is just like what you see. If you have some fluid jet, a fluid jet also develops these ripples. You can see them when you go to the heat sensing. You see the fluid jet that's breaking into the droplets. Well, what we say is that the process is the same. How does a fluid jet break up? Well, it's driven also by some classical hydrodynamic evolution. Then it forms a neck. Then the neck is something where you have a large surface tension, like surface gravity, and then this neck with a large surface tension, you don't describe it using hydrodynamics, you describe it using molecular dynamics, and this molecular dynamics, what it does is evaporate the neck. I need a few molecules.
Can I make just a comment about that? Because that analogy, I think, is in a sense, if you use holography, anyway, it is exactly describing the breakup of two black holes, right? The breakup of a black hole.
Yeah.
Right. So in holography, drop of fluid is a black hole. So if I split a
Yes.
drop of fluid, I split a black hole.
Yes, I think one can go. I mean, I say a few more things about holography, and I would like. I would be interested in knowing exactly what you have in mind because I thought about. But yeah, this is one case where I think one can make it more precise. In fact, I think that one can make it even more precise, mathematically quite precise, because we think that the theory in hydrodynamics of fluid jet breakup can be adapted to describe the breakup of the black string. But after the breakup, so you have the fluid jet or the black string, it breaks, then you form droplets, you form separate black holes, and then they just evolve following the laws of classical general relativity. You only need to say what's going to break this up. Classical general relativity is not telling you, but then you cut it by hand. I mean, whatever you do, it's going to be something that's going to involve just a tiny disruption to the entire process. Tiny, when I mean tiny, is something that's suppressed by the ratio between, or a power of the ratio between the Planck mass and the total mass. So that's an evolution that's it's essentially governed by classical dynamics up to just some tiny effect. So in the case of the collision, this is what we think will happen. This is something that we've done using this largely effective theory. Can tell you more details about it. How do we regulate in this case the moment of
This, I mean, normal black holes, 3+1.
Yes.
We say that you cannot split a black hole because of the area theorem. Here, I guess, because of the higher dimensions and the fact that it's a rod, you're able to do it. That's how you can do it.
So there are two reasons that black holes cannot bifurcate. One of them is, so there's a general theorem which doesn't even, I mean, Penrose proved that if you assume cosmic censorship, then future event horizons don't bifurcate. This doesn't even assume energy conditions nor equations nor nothing. Then what you say is right. If you collide, say, two black holes, two sources black holes, then, I mean, in order to split them back, you would need to violate the area theorem. Now, in this case, this is something that's allowed. I mean, there's no the area theorem allowed.
Because of the higher dimension.
Yes, exactly.
But you're necessarily breaking GR though.
You're necessarily breaking GR at the moment of yeah. So this evolution needs that at some point, if you're doing some numerical evolution of this, then at some point, well, when you end your when your code crashes, then you go, you take your data, then you do something by hand, and then you let it evolve.
So it's even in higher dimensions, classical GR doesn't allow the horizon to snap.
That's right. I mean, this is a generic theorem that Penrose proved that doesn't require almost anything, just the definition of event horizon.
So,
is there a naked singularity here?
There's something. It's regulated. So there's a regulator in our construction that allows you to proceed here. Okay, so we don't really form a naked singularity. We form a region where things are large, but not never in.
When 3+1 dimensional black holes are merging,
yes,
the shape of the event horizon at some instant starts to become quite distorted, and does it actually form a neck at some point?
No, in 4 dimensions, no. I mean, they form a common horizon, and then this relaxes back to equilibrium.
But right before they merge, there's a little. They look a little bit like teardrops, and then.
Yeah, the event horizon, yes.
But then they do connect at some.
Yes.
So if that's not a neck, there is some sort of.
Yes, but the curvature there is perfectly smooth.
Okay.
I mean, so that's something that, in fact, I mean, I can give you a very simple, exact model of that neck.
Not neck, so it's not a neck.
Well, the neck, the point where the two event horizons. That's something that can be described in an exact way.
And there's no way to just fine tune the masses of black hole in such a way that it actually does start looking elongated. Or...
No, in those cases, I mean, what you can find is some slicings where the topology may be different, but the curvature there is fine.
Regardless of all of the mass. Okay.
Yeah, all curvatures are of the same scale of the mass of the black hole. So then, if what I've been telling you is correct, I mean, I've made an assumption about quantum gravity, right? That quantum gravity affects this breakup, which to me it's the only plausible evolution. But if this is correct, then these violations of cosmic censorship are essentially harmless because we're preserving predictivity. Then we've only had to introduce this tiny effect, but the loss of accuracy is something that's parametrically small. This, or even less, because I think many of these processes are actually controlled by classical attractors, which means that the accuracy loss may be even less than So we can evolve, we can start with smooth initial data, we form the naked singularity, then, well, we let it, we fix it by quantum gravity effects, but then afterwards the evolution still proceeds as classical gravity process. So even if in these examples of cosmic sensor violation, we have a violation of cosmic sensors, right? We formed, starting from smooth initial data, we have formed a region where there's a Planckian energy density. So CC is violated in letter, but the spirit is still alive. I mean, we can use classical general relativity to follow this process. Now this is for mild violations, okay? The ones with strength index equals 0. Are there examples of violations with a strength index larger than 0? Well, until recently there weren't any that I could say that they are convincing. But now there's this example that Gary Horowitz with George Santos, Benson Way, and then also involved in Crisford, student. They say that they have an example which, well, understanding the singularity here is something that I've been discussing with them, with George Santos. I'm not sure whether, I think that now George is saying that this is an example of a strong violation, a bad violation, but then they have this idea that this example might be ruled out by the weak gravity conjunction. This is something that I know about. I think one has to understand better what the singularity is and what its structure is doing, what the singularity is doing, before reaching any conclusion about how bad, how serious the loss of predictivity is in this case. But in any case, I think that it's interesting that for me, beyond the weak gravity conjecture, and the idea that if you have a violation, a strong violation of cosmic censorship, bad violation, this could, let's say at the beginning, could violate entropy bounds. Because you're concentrating too much information into too small a space. And if you're violating entropy bounds, then you might be worried whether you're violating something about thermodynamics. So maybe violations of this could be forbidden by something that general principle like the laws of thermodynamics. And then, well, I don't have anything much to say about this, but I think maybe cosmic censorship after all is a consequence of thermodynamics. That's something that I think is worth exploring more. But well, on this note, I'll stop and thank you.
So you characterize cosmic censorship, or at least motivated by talking about predictivity, but all your examples focus on high energy violations. But it's extremely easy to construct using well-known spacetimes examples where you have a maximal globally hyperbolic development that is still itself extendable, but is extendable non-uniquely. So the globally hyperbolic quadrocosmos spacetime, Gaudy spacetime, tutorial spatial cross sections. These are maximal globally hyperbolic spacetimes, but you can extend them in several different ways, none of which are isometric to each other. I mean, isn't that like a more serious worry about prediction than these examples, or these series?
I'm not sure. I mean, so those wouldn't count as violations of the cosmic censorship, right?
That's what I'm trying to figure out on this too, because you talk about predictivity, but then you also talk about high energy. So I'm not sure what the relationship is.
So here I'm worried about predictivity, loss of predictivity, or worried or excited about the loss of predictivity, because you're exploring a quantum gravitational regime. Whereas in the examples that you're talking about, I don't think that
there's no high energy.
It's a different kind of loss of predictivity, which is also something that maybe I think it can be very interesting and important, but it's a different kind of problem, right?
There's no also if something's kind of asymptotically flat, sort of violations, it's a different motivation.
Yeah, I think it's a different kind of problem. I'm not saying that, but the problem of whether we can access a regime of quantum gravity, maybe what I'm asking here is, well, what do we want a theory of quantum gravity for? If we can never access a regime where quantum gravity, I mean, the only regimes where quantum gravity is important are these regimes where you have a few Planck masses within a Planck volume, which are going to last a few Planck times. Well, I mean, that's something we want to understand better. But whereas if you had larger amounts of Planck energy in a small region, then that would be something that quantum gravity would be definitely really very important.
I want to understand this S index a little better. So let's imagine that I've got some object which is not a black hole. It is singular at the origin, so it's some power law distribution of density or whatever, it's got some radius.
Yes.
So I've got infinite density right at the core.
Yes.
So there's very little mass.
Yes.
And there's a total mass m when I look at everything.
Yes.
Now I want to calculate S.
Yes.
For that I need to know where to put a boundary and say that this is my naked singularity. So what criterion do you use?
I will put it at the Planck length because I don't want infinities.
Okay, so
I use always some cutoff, and then at the Planck length, I think that in your example I will have a Planck mass. So that would be S equals.
That will depend probably on the.
It may depend. Yeah, it may be. Yeah, if it's steep enough, maybe you can get something that's larger.
Okay.
Yes.
And then you would consider that a stronger violation.
It could be. You can form that starting from initial data. Then I think that smooth initial data and reasonable matter or whatever. I mean, you specify. The rules of the
So
game.
you're not just saying it's the Planck mass, it's a Planck radius.
Yes.
So however much mass you include in a Planck radius will be called.
So in the case that you're talking about, that's a singularity that's not isolated from other sources of mass, right? So then in that case one has to, I think one has to play the game of being physics guided and trying to be
Right. So I can think of many criteria you can use. Maybe a curvature related criterion.
Yeah, it could be. There are different criteria, and then one has to see which one
Each
is.
will give a different S.
Yeah, it may be. Well, if they give different S, then that would be interesting.
Okay.
If they don't give the same S, then.
But that's also interesting. Okay.
So if you look at these naked singularities, like the Christodoulou constructed, right, in Einstein scalar field symmetry, these are not sort of zero mass singularities. They have there's some threshold they can't be, but
Are these ones are they related to the Choklik?
I don't know because the Choklik ones are sort of zero mass, right?
Yeah, I'm not sure.
I think they're quite different. They're very different.
And you form them from smooth initial data, or
well, not smooth, but okay, you can have some discussion about.
Okay,
but anyway, but the claim is that one should consider them as naked singularities. But they're not zero mass.
Okay.
The Hawking mass is.
Okay, the Hawking mass is.
So
then that's interesting because I want to know different examples because it's not that I'm saying that since the last word on these mind similarities, but if there are examples of other things, I think it's interesting to understand them from a perspective. I mean, I think that this perspective of how strong the similarity is, how bad the loss of predictivity, if it's a mild singularity that in some sense we can just fix with some, it's what I sometimes call as quantum gravity pixie dust, and you form this object and then you throw some pixie dust and then you let the system evolve. If you need something that's more than just this mild pixie dust, then I think it's interesting because it's telling us something about I think it may have implications for holography. This violation that Yakov and collaborators are describing, I think we should try to understand it better from the point of view of holography, in particular because they are finding it in ADS. So, and what it means, I think it's important.
Great, let's send you out speaker again.
threshold. I can't quantify.
Yeah.
Another thing is also, so I guess, so right now, they have these different kinds of critical phenomena.
It's a very bright jacket you got.
Yeah, so these top tier ones are like the exact two of them, sort of zero. But they're like, whatever you glass on something,
Yeah, there's also for different types of matter, but I think that
I don't know this very well, but I don't know if it's positive. It might still be
really
small.
I think that they are all, I mean, if it's critical,
Come on.
what